Let's say that I'm focusing on this right triangle. It doesn't matter which one you focus on. They're all congruent. We just got done saying that and proving that. What is printed on this piece, or what is given, printed here, is the height printed, written on the board?
Nope.
No. Can we find it?
Yes.
Using?
Pythagorean's theorem.
Pythagorean's theorem. So when you use Pythagorean's theorem, because if this guy over here is 5, that means this over here is 5. After using Pythagorean's theorem, what is the length of the other leg of this right triangle?
4.
It is 4. Did anyone not have to do math at all to figure that out? How, Ellis?
It's just one of the common right triangles.
Yes, it is a Pythagorean triple. This is one of the common Pythagorean triples. It is a 3, 4, 5 triangle. And like I said, it does show up on like SATs and stuff like that. So it'll save you a little bit of time on some tests. Cool, so we can simplify all of these whole numbers. 4 times 1/2 times 3 times 4. And if we do that correctly, we should get 24 units squared, correct? Yeah, okay,
Yes.
cool. Okay, awesome, thank you, yes. Now, we want to, we're not going to do this every single time. Like, there's got to be an easier way. And there has to be a way to relate it to a rhombus. We have to take this and put it in terms of a rhombus. The rhombus has 2 diagonals. I'm going to call the shorter one D1, diagonal 1. I'm going to call the longer one D2. So we have to understand that this is the entire diagonal. This is D2, all the way from tip top to the bottom. And then this horizontal, this whole thing is D1. I want to take this 4 times 1/2 times the base times the height of the triangle, and we're going to put it in terms that relate to parts of the rhombus. So we had 4 times 1/2, and then we put in 3, which was the base of one of those right triangles. But that segment that was 3 units long, how could you describe that using the diagonals?
It's 6 units long.
How could, but we can't change it to 6. It's got to be 3. So what could we write here to put it in terms of the diagonals? How did you describe this segment right here?
It's 1/2 D1.
It's half of this diagonal. You okay with that? The whole thing, this whole thing is D1. Then that segment that is 3 units, or that was 3 units long, that is 1/2 of D1. Okay, my diagonals, these are the whole things. That's a whole diagonal right here. And this very long segment all the way down, that's a whole diagonal. The other value is the height of that right triangle, which was 4 units long. So the segment that's 4 units long, how could you describe it? How could you put it in terms of the diagonals and the rhombus? Because that's what we need. We need a formula for the rhombus. How could you do that? 1/2 of D2. So right now, this has nothing to do with the triangle anymore. Like we are now relating it to the shape, the rhombus. And so everything is in terms of the rhombus, D1 and D2. That's the diameter, the 2 diameters of a rhombus. So now we're not talking about these triangles anymore, because we want something that deals with the rhombus. Let's simplify these coefficients. We're multiplying all 6 of these values. 4 times 1/2 times 1/2 times D1 times 1/2 times D2. So let's simplify all of those coefficients, all those numbers. So can someone tell me what 4 times 1/2 times 1/2 times 1/2 is? Oh, put your calculators down. Come on. What's 1/2 of 4? 2. Okay? That's 2. What's 1/2 of 2?
1.
What's 1/2 times 1?
1/2.
1/2. Okay? So 4 times 1/2 is 2. 2 times 1/2 is 1. 1 times 1/2 is 1/2. So we've just simplified those coefficients. And then we had D1 and D2. So that is 1/2 times D1 times D2 on your formula chart. That is where the formula comes from. Because someone figured out and saw the pattern that, hey, we can just find the area of these right triangles and then multiply by 4. And then someone came along and said, well, that's the same exact thing as taking 1/2 times D1 times D2, because your base and your height, they're always going to be half of those diameters. So now we don't have to go through that process anymore. We can just take the product of the diameters and divide by 2. And we've got the area of the whole rhombus. The next one.
Trapezoid.
Trapezoid. So in your notes, so the next formula in the formula chart is for a trapezoid. I think when we see or think of a trapezoid, it's always like this, where the top base is always much much shorter than the bottom base, and it extends on both sides. But on this homework this evening, you're going to find a lot of problems like this, where this is a trapezoid, and it doesn't look like the traditional one. By definition, what do we know about a trapezoid?
It has one pair of lines.
Okay. One pair of opposite sides are parallel. By definition, if I said these are trapezoids, then we know that those are parallel. So what is the measure of this angle then? It would have to be 90. Why?
Because
I need the
if lines are parallel, then same side interior angles are supplementary.
Good. If lines are parallel, then same side interior angles are supplementary. Again, blast from the past, but your final, it's all of this. It's all of this. So yes, if lines are parallel, because that's what we know, then we can conclude that same side interior angles are supplementary. So if one is 90 degrees, the other one must be. Awesome. That's going to come into play because you have B1 and B2. You have B1 and B2. Those are the lengths of your two bases. Those are the sides that are parallel. You need a height. Is this the height of this trapezoid over here, this leg? Why not?
Because it's not perpendicular.
It's not perpendicular. Like we said earlier with the parallelogram, the base and the height must always be perpendicular. So when you get a shape like this, you need to understand that that is your height. It's going to be perpendicular to both of the bases, and it's the distance between those, the perpendicular distance between those two bases. But you need to be able to place this height in a strategic place. Like that doesn't really do us any good. However, if we place it at this vertex and go straight down, then what we've done is created a right triangle over here that we could possibly solve and get the height. That's the same thing here. If I add in an auxiliary segment that is perpendicular and it comes from this vertex, I've now broken up this trapezoid into two shapes, a rectangle and a right triangle. And so we'll use that to help us solve for the area, solve for the height and then get the area. Real quick explanation of the formula. If I draw in one of these diagonals, and it doesn't matter which one, I'll draw top left to bottom right. On this one, I'll draw bottom left to top right on that one. When you draw one of the diagonals in these trapezoids, what does it break that shape up into?
Two triangles.
Two triangles. So if I wanted to find, let's say we didn't know the formula for a trapezoid, then what we could do is say, okay, I don't know how to find the area of the trapezoid, but I know that I can find the area of this triangle and add it to the area of this triangle. Let's see what happens. Area of TRAP, trapezoid. If we wanted to, we could take the area of those two triangles. Area of a triangle is base times height, correct? Sorry, 1/2 times base times height. Look at those two triangles in the trapezoid. other than them sharing that side, what else do those triangles have in common? Other than having a common side, what do these two triangles have in common? Okay, we have one pair of sides that are parallel. That has to do more with the trapezoid than these individual triangles, but that is true.
An altitude.
They have a common altitude. Where's the common altitude for those two triangles? What do you mean by altitude? You're closer. What does altitude mean when we hear that?
It's from the highest point down to the lowest.
Okay, so highest to the perpendicular side, but it means height.
Oh.
So these triangles both not share the same height. This triangle and that triangle have the same exact height. These two triangles have the same exact height, correct? Okay. So the only thing that's different about those two are the bases. So I have area of the trapezoid is equal to 1/2 times one of those triangles, its base is B1. The other triangle, its base is B2. But they have the same exact height. In Algebra 1, you should have done something where it was the opposite of distributing. It was the opposite of that. Does anyone remember what you call that? What's that?
Factoring.
Factoring, okay? You can factor out from two or more terms if they have a common factor. That's why we call them that. So if we look at this, at these two terms, 1/2 B1H and 1/2 B2H, can we factor anything out from those two terms that they have in common? H, what else? What else do those have in common?
1/2.
They also have 1/2. So if I distribute the 1/2 to those two terms, and then I distribute the H to both terms, I would get right back here. The area of these two triangles added up. Well, if you look at the formula chart, our formula chart just says that the area of the trapezoid is 1/2, sum up the bases, and then multiply it by the height. And that is why. So you can just break it up into two triangles, and this is what happens every single time. Every single time. Really quickly, I want to look at two problems on your workbook page packet that's for homework. Please turn to page 22, 207, number 22. 207, number 22. What shape is that?
Trapezoid. Oh wait, no. Pear?
What is that shape? The whole shaded region?